Thank you for the introduction. Hi, everybody. Today I'm going to talk about Fractal and how it provides bolt-on fault tolerance for a system that distributes opaque components of unmodified shell programs. Today's software systems often compose opaque components to accomplish complex tasks. As the name suggests, these components interact with each other through diverse communication mechanisms, such as raw data streams or well-defined protocols, without exposing their internal states and execution logic. While this composition is powerful, the opacity complicates the fault tolerance in distributed execution of these components. There are many such environments, such as microservices or agentic workflows. In this talk, we focus on the shell as a concrete and pervasive example across various domains, such as bioinformatics analysis, data science, and even agentic workflows. Over the past few decades, extensive work has improved the runtime performance of shell programs, from single-node acceleration to distributed executions on platforms such as distributed file system and serverless. However, none of these distributed executions is fault-tolerant. Let's take a look at an example pipeline that utilizes multiple opaque components to analyze network logs from Nginx servers. This pipeline iterates over files stored in Hadoop distributed file system, filters requests generated by known search bots, extracts the IP, calculates the visit frequency, and finally sorts the result to identify the most active bot IPs. To make this pipeline fault-tolerant at scale, a natural approach would be to rewrite the pipeline using existing fault-tolerant frameworks. For example, building data lineage using resilient distributed dataset abstraction in Spark, or implementing mappers and reducers in Hadoop Streaming. However, this would require rewriting all the programs manually to use the primitives exposed by these systems, forgoing the benefit using existing components opaquely and expressing only a subset of the computation while leaving the surrounding pre-processing and post-processing in the shell. This manual process is not just time-consuming, but could also easily go wrong with human errors because shell programs dynamically interact with the environment and compose heterogeneous tools. Is it possible to directly bolt fault tolerance onto the systems we mentioned earlier that efficiently distribute unmodified shell programs? Before we answer the question, let's go back to the pipeline to see how distributed execution works for this shell pipeline. Given the program from the client, a distribution system first converts the pipeline into a data flow graph, and then distributes parallelizable computations such as filtering and extraction on individual distributed file system data blocks across worker machines. And then it aggregates the result on one of the workers and finally streams the output back to the client machine. Unfortunately, tolerating fault in this distributed execution is challenging when using existing fault tolerance techniques. One idea would be to checkpoint and recover from all the program states. However, all these components can maintain opaque states. For example, the grab command maintains line-level states for its internal meshing, and the sort command buffers the entire input before producing output. Because all these states are completely opaque to the system, so it is very difficult, if not impossible, to checkpoint and recover from all these intermediate states correctly. Alternatively, we can also consider barrier-based solution or lineage-based solution. These approaches typically require an explicit stage to observe the progress or structured data or task to replay the failed computation. However, in this distributed execution, all these components interact with each other through raw data streams without structure or metadata. So the system cannot track the progress through the pipeline and know where to recover after a fault. To resolve all these challenges, we introduced Fractal, the first system that provides fault tolerance for distribution of shell programs. Crucially, it directly bolts on systems that distribute these opaque components in unmodified shell programs. Fractal focuses on the fail-stop or fail-restart crashes of these worker nodes. These workers execute long-running, deterministic, and idempotent computation for parallelism. Side-effectful and non-idempotent operations, such as output redirection or interacting with the client file system or environment, directly run on the client machine. The goal of the fault tolerance is that even under faulty conditions, the execution has exactly the same behavior, such as the ASIC codes, and produce the exactly same output without duplicates or loss of data. The key insight in Fractal is that it operates at the level of subgraph, defined as the complete program fragment assigned to a single worker. Each subgraph only reads data from in the distributed file system or outputs from other subgraphs, and only writes output across the worker boundaries to other subgraphs, to other workers or the client machine. Fractal treats each subgraph as a completely opaque computation without requiring inspecting the internal states of individual commands. It only tracks the execution at the input and output boundary for each subgraph. For example, the input data boundary at the distributed file system and communication boundary between subgraphs. Building on this insight, Fractal introduces a series of mechanisms to enable faster recovery transparently. First, it directly boasts the progress tracking on these communication boundaries over raw data bytes. It introduces remote pipes, a drop-in replacement for Unix pipes in the shell programs. During normal execution, these remote pipes periodically report the progress to a logically centralized monitor, such as the number of bytes it has received and sent so far. All this information will be used during recovery to detect and discard duplicates, ensuring exactly once delivery. Fractal also introduces a series of runtime optimizations to enable fast recovery while balancing the overhead during fault-free execution. For example, it selectively decides whether to persist output of a subgraph depending on cluster information, such as available disk capacity, and subgraph characteristics, such as the actual input data size. Finally, upon detecting a fault, Fractal classifies these subgraphs into two different categories and apply different recovery strategies. First, regular subgraphs that operate on individual data blocks. And second, merger subgraphs that aggregate multiple results from the regular subgraphs. The key to the recovery is to use the same input to reproduce the output of a failed computation. Specifically, to recover from a regular fault, Fractal simply re-executes the computation on the same distributed file system input data block. To recover from merger faults, Fractal ensures that all missing input are correctly regenerated, either by directly reading the persisted output on the disk or re-executing the upstream subgraph when the output is not persisted. And all the duplicate data will be detected and removed by the remote pipes. Because Fractal boasts on the state-of-the-art shell distribution system, the evaluation focuses on the performance of Fractal under both fault-free execution and faulty recovery. In the evaluation, we use 5 benchmarks from the Koala benchmark suite, totaling 77 scripts and up to 33.4 gigabyte input data. We compare Fractal against Bash, the standard single-node shell interpreter, Dish, the state-of-the-art shell distribution system that Fractal boasts on, and Apache Hadoop Streaming, a MapReduce-based system that offers fault-tolerant distributed execution of arbitrary binaries, including the Unix command used in the shell programs. We also introduced Frac, a fault injection subsystem that enables injecting faults at precise progress points. Now, let's first take a look at the fault-free performance of Fractal in a 30-node cluster. The x-axis here is the speedup over Bash, and the left y-axis is the density, or the PDF, of the speedup across all benchmarks, represented by the shaded area here. It captures the overall distribution of speedups across all the benchmarks. And the right y-axis represents the proportion, cumulative proportion, or the CDF of the speedups, represented by the solid lines here. It indicates the fraction of the benchmarks that achieve at least a given speedup. The further to the right the plot is, the system achieves higher speedup in more benchmarks. Compared to Hadoop Streaming, Fractal achieves substantial speedups. For example, it achieves up to 107 times runtime improvement, where Hadoop streaming only achieves up to 9.5 times. This is primarily because Fractal exploits all parallelism, including data, task, and pipeline parallelism across the entire shell program, whereas Hadoop streaming enforces rigid MapReduce stages, ensuring that all mappers and reducers complete before the next stage can begin. Fractal introduces slowdown in a small subset of the benchmarks when the distribution overhead dominates the execution. For example, when the input data size is small or the computation is trivial. How does Fractal compare to Dish? It achieves comparable performance to Dish, demonstrating that extra component to support fault tolerance introduce very little overhead in fault-free execution. In some cases, Fractal even outperforms Dish because of a series of runtime optimizations. To evaluate the fault recovery performance, let's zoom in on a script that contains a single pipeline calculating the top n frequent words in the large text input on a four-node cluster. The x-axis here is the total execution time, and we compare Fractal against Hadoop streaming. In fault-free execution, Fractal is more than 3 times faster than Hadoop streaming. We first inject faults at 10% completion time, where both systems are either executing the regular subgraphs or the mappers. In this case, Hadoop streaming takes about 94 seconds extra time to recover from the fault, and Fractal takes about 36 seconds extra time to recover from the fault. In this case, both systems recompute only effective computation while preserving the parallelism across the entire program. We also inject faults at 90% completion when both systems are close to completion, executing either the merger subgraphs or the reducers. In this case, Hadoop streaming takes about more than 1,000 seconds to recover, and Fractal takes about more than 220 seconds. It is important to note that both systems take longer than a full re-execution in this case, but this represents the worst-case scenario because both systems require re-executing more computation to regenerate the missing input for the merger subgraphs or the reducer. We cover more system designs and results in the paper, including runtime optimization, such as event loop execution, and fine-grained performance and recovery analysis in different scales of clusters, and a set of micro-benchmarks to evaluate the design choices of Fractal. To summarize, in this talk, we introduced Fractal, the first fault-tolerant distribution of unmodified shell programs. It introduces a series of runtime optimizations to enable fast recovery, and a fault injection subsystem to enable large-scale characterization of fault recovery. Fractal is open sourced. Feel free to check it out, use it, and provide feedback. I'm happy to take any questions. Thank you.